Hello, it's Keith here, and this is lesson 2 of the Hello World series of my MIPS assembly programming tutorials, and today we're going to be making a Hello World on the PlayStation, and I've forgotten to load it because I'm very silly. Here we go, that's what we're going to be creating today. So we're going to be showing the Hello World message onto our screen, and we're using our own font, and we're going to create our own cartridge, and we're going to learn how to assemble that with our assembler and then run it with our emulator. So let's go straight over into our source code and let's take a peek. We'll see what we've got. Okay, so here is the file. The first one we're going to try out is PSX Hello World. And so the first thing we're doing is we are basically telling our assembler what kind of system we're assembling for, and we're telling it .psx, that's an assembler directive. Now the assembler we're using today is the RMIPS assembler. So that's what we're using, and that uses that special assembler directive to tell it what system to develop for. Now we are creating a binary file, and that binary file is going to be loaded in at the memory address here. So we're specifying that here, and then we're setting the origin of our code here. Now what we're then doing next is we're going to define two parameters. Now when it comes to drawing to the screen, the way I always do things in my tutorials is I create a print char routine which shows a single character to the screen, and then I extend that into the other things that I require, like a print string routine to show a string to the screen, or a monitor routine to show a contents of a register to the screen. So I always work in this way of working. I essentially try and treat it as close to an 8-bit system as possible. So all we've got is a simple routine to print one character to the screen, and that means after each character we need to remember where the next character is going to go as we print our string. So we're defining an X and a Y position for our cursor, and these are going to be 1 byte parameters, and we are loading these into memory addresses, basically offsets to the user RAM. So this is our RAM that is available to us, and we're defining this as the RAM that our program is going to use, and these offsets in that RAM are going to be used for our cursor X and Y position. We'll see those later on. So that's what we're doing there. Now the first thing we're going to need to do is we're going to need to set our graphics hardware. Now we're basically going to set the A0 register, we're loading the upper immediate, and we're loading 1F80 into the top 4 nibbles of our memory address. So we're going to be using various addresses from that 1F80 range here. You can see 1F801814. We're going to be using quite a lot. That's access to the screen hardware, but we are going to be using 10 as well and things. So as I say, the base, we are loading that 2-byte value into the top half of the 32-bit value in A0 there. So we're loading that in there. Now what we're then going to basically do is we're going to set up our screen area. First we're going to set the screen mode itself, and this requires us to send a large number of weird and wonderful parameters to offset 1814 of the IO base there, and so we're sending all of these. That is setting up our screen. Our screen is basically going to be 320 by 240, 16-bit per pixel, which means 2 bytes per pixel. So this is setting up that screen there, and then what we're doing next is we're basically setting up what's defined as the screen area, and this is relating to some of the rendering commands, and all we're doing is we're setting the area to be the entire screen. So we're just setting the top corner 0,0 and the bottom corners 320 by 240. So that's what we're doing there, and this is just to make sure we can use the screen in a reasonably simple way, shall we say. Okay, once we've done that, we're just loading our stack pointer, pointing to the start of the user RAM there as the stack. That will go down in memory, and then what we're going to do next is we're going to do a few things as part of our test program. We're going to clear the screen. We're going to clear the screen blue. We're then going to show the text message. We're loading the address of text into A0, and we're running this print string routine we've written. We're then going to create a new line, and then we're going to show the string again, and we're doing that because if the print string routine crashed, we'd never get to that second print string. So by showing it twice, we know that our program is actually executing to completion, hopefully. Once we've done that, we've just got a simple infinite loop here, and that is just basically locking up the processor. So our program's finished. We're on an emulator, so we'll just close the program once we're done. Now that's what we're doing there. Now the text string we're showing is this text string here, which is a sequence of 8-bit bytes here. Hello world, the message in ASCII there. And there's a 255 byte at the end. Now in my tutorials I always use 255 termination. You may prefer 0 termination, that's more common, I know, so if you want that you can just change it to a 0, it's not too hard. But as I say, for consistency across all my tutorials, I started using 255, and so that's what I've continued using. And we've got an align command because we want to be 32-bit aligned for our commands. So after any kind of data, which is in the middle of our program code, we've got a line 4 there to align to a 32-bit boundary there. Okay. So first of all, let's take a look at our print string routine. It's a nice simple thing. So the print string routine, basically, what we're doing is we're backing up the return address because we're going to call the subroutine print char. And all we're doing is we're loading an unsigned byte into A1 from A0. We're then moving A0 across by 1 byte. We're seeing if that byte is A255, and if it is, we're done. And in that case, we just restore the return address and return. If not, we pass it to the print char routine and we repeat until we're done. Okay, so that's how we're printing the string. The new line is very simple. We're loading the address of our user RAM into T7 here, and we are basically loading the current Y position. That is the character Y position. We're adding 1 to it, moving us down by 1 character, and we're loading a 0 into the X position. So we're moving down 1 line and moving back to the left. So new line, carriage return, if you will. That's what we're doing there with that new line command. Okay, we'll look at the print char routine later. It's a little bit more complicated. I want to cover the CLS routine first because it's a little bit simpler. Now, when it comes to graphics on the PlayStation, we can't directly access the memory like we can on the N64 and on 8-bit systems. So the video hardware is controlling the memory, and we need to tell the video hardware a sequence of commands and tell it what we actually want to do, and the video hardware will do that for us. Very much like the MSX2, strangely enough. So what we want to do here is we want to fill the screen. So what we want to do is we want to define an area, and we want to define a color, and we want to tell the graphics hardware to get on with it. We're not going to do the work. We're not going to plot the pixels. The graphics hardware is doing it for us. The benefit of this is it's fast. The disadvantage of this is, well, you know, personally, I like to actually get down and dirty and mess with those pixels, and it won't let us, so we can't. Anyway, what we're going to do here is we are going to define our command. Now, our CLS command, basically, we need to do a sequence of things. The first thing is we need to define the command number. Now, this is the top byte here. O2 is the fill command. The remaining bytes here are the blue, green, and red values, and each of those is 1 byte. So 7F is kind of mid-blue, and green and red are 0 there. But we could mess around. If we move the 7F here to all the way over here, and we run again, well, we're going to get a rather ugly display, I think. I think we will. So there you go, we got a nasty red now, but you can see the hello world is still in yellow on blue. And the reason for that is that our font drawing routine is drawing the blue background there. So we can specify basically any color we want there, and we're sending that to the graphics hardware GP0 port here. That's 1810 offset into A0. Now A0 actually, a bit sloppy there. A0 actually does need to still be set to the IO base there, so let's do that correctly. We don't necessarily know that the clear screen command is immediately being run, so let's load A0 back in there. That's better. So that's what we're doing there. We're first specifying the command and the color. We're then specifying the start X and Y, 0, 0, and we're then specifying the width and the height. Now, I believe from later testing here that the X coordinate needs to be a multiple of 16 pixels. I guess that's the way the fill command works. It doesn't. It's probably doing some bulk copy in words, bulk fill in words, and maybe the bit plane organized means that it has to be a multiple of 16 pixels, I guess. Anyway, just something to bear in mind if you're trying to fill weird areas there. But we're specifying the start as 0, 0. You can see there's 16 bits for the X position and the Y position here. And then we've got the width and the height here, and you can see we've got EF by 13F, and that is actually 239 by 319, and the height is the first 16-bit value there, the EF, and the width is the 13F there. So once we've transferred those, that actually does the fill for us, and then all we're doing after that is we're loading a 0 into our X and Y position for our cursor. So that's how we're clearing the screen. Well, the next question is, well, how are we actually drawing the character? So we're running this print char routine with a character in the A1 register, and that's the character we want to show to the screen. Now, there's some limitations. Now, basically, we've got a bitmap font that I've defined, and I use the same font in all of my tutorials, including the 8-bit ones. So it's 1 bit per pixel, 8 by 8 pixels font, and that means that one line of our font is a single byte. Now, there's another thing, and that this font has no characters below space. Now, space is character 32 in ASCII. So what we need to do is we need to calculate the offset of the character we've been asked to show within our font. So the first thing we're doing is we're subtracting 32 because the first character in our font is character 32. We're then loading in the address of the font, my font, which you can see is that here. We're then basically taking the character number once we've subtracted 32, and we're effectively multiplying it by 8 because there's 8 lines and also 8 bytes for our font characters. So each character is 8 bytes. Character number minus 32 times 8 is the offset to our font. So once we've done this, we've calculated the offset for the character we want to show. What we next need to do is work out our destination on the screen. So what we're doing here is we're taking our X position in characters, multiplying that by 8, and now we've got our X position in pixels. Now we're taking our Y position in characters, multiplying it by 8, and we've now got our Y position in lines. Now again, just like when we cleared the screen, we're going to have to tell the graphics hardware what we want to do. Basically what we need to do is, like with that fill, we need to specify a corner position and a width and a height, and then we're going to send the pixel data to the GPU graphics hardware, and that will draw it to the screen. That's what we're going to have to do. So once again, we're loading our IO base here into T4 this time. We're using different registers just for convenience. And basically, we're going to have to send a sequence of commands. Now, the command we're using this time is A0. So the top byte is A0 there. You may remember before that it was 02. Now it's A0. So that's a different command. And this is, I believe it's called send image to frame buffer. So we're sending graphics to the graphics hardware here. And then basically what we're going to do next is we're going to need to specify the X and the Y position, with the X position in the low half and the Y position in the high half of the 32-bit value. And so we're just doing that with a shift of our Y position by 16 bits and then adding the X position, and we're sending that word to the graphics hardware there. Okay, we now need to send the width and the height. We need to send the height first and then the width. Well, it doesn't really matter because our height and the width are 8 by 8 pixels, so we're just sending that there. Now this has now set up the area of the screen that we're going to draw our character to, but the graphics hardware doesn't know the characters. We're actually going to send them now as bitmap data. So now that we've defined the area, we can now just send the individual pixels that make up that character. That's what we're going to do here. So we're specifying the height of our character in lines. Now remember, there's 1 byte per line. We're then specifying the width. Now that says 4. It says width in pixels here, but it's actually pairs of pixels. I will change that. Pairs of pixels. There we go. The way the PlayStation works, we actually have to send 2 pixels with each write, because each pixel is 16 bits, but we have to send 32 bits at a time. So we're working in pairs of pixels here. So that's why we've got a value of 4 there. What we're doing next is we are loading in a single byte from our source font here, and we're moving across 1 byte, effectively down 1 line of our font character by incrementing T6 by 1 there. Okay, now what we're going to do next is basically we're going to transfer 2 pixels from our source font into a value and then send that value to the graphics hardware. Now we're going to use 2 possible colors. We're going to use a color for if the pixel is clear, a blue color, that's that color there, or a color if the color pixel is set, which is a yellow, that value there. And so what we're doing here is we're loading our default value into T5 here, and then we're testing effectively pixel 2 here, which kind of looks backwards. We're effectively testing bit 6 rather than bit 7, which is the second to the leftmost bit, and the reason for that is that the values in our 32-bit word are kind of the other way around, and so that's the way I decided to do it for this. So we're testing that second bit there, and if it's clear, then we're using this value here, but if it's set, we're using this value here. We're then shifting that to the left by 16 bits, moving that into the high 16-bit value, the high half of the 32-bit value in T5 there. And then we're testing the bit 7, the topmost bit, which is, as I say, kind of the other way around. And what we're basically going to do is, depending on if that bit is set or clear, we're going to OR in a yellow pixel or a blue pixel into the low half of that 32-bit value. So we've now set the 2 pixels within the 32-bit value, and we're now going to send that data to the video hardware, and that will effectively eventually plot it to the screen. And I don't think it's not going to be instant because of the VBlank, but it's going to come very quickly. So that's what we're doing there. We're then decreasing our X counter, and we're repeating to do the next pair of characters here. So we're transferring another word to the video hardware there, and we're going to do that 4 times using 2 bits from our source font each time. And then once we've done that, basically we are going to repeat and do the next line. What we're going to do next is we're going to load in our X position here, and we're going to add 1 to the X position, effectively moving us across 1 character, and that's so that next time we draw a character, it's going to be 1 position along on the screen. So there we go. That's how we've got our example that we saw before. And there we go, that's how we can get Hello World to the screen. Now we're not quite done yet. We are going to see a couple of other things. We're going to look at how we actually assemble that, but the first thing I want to show you before I do that is this advanced version. Now we're not going to go into the code of this one because this is just as sort of a bonus. In all of my tutorials, this is what I do when I'm learning a new system. I try and get hello world on the screen, and then I try and get the contents of the registers and the memory on the screen, because if I can see what the registers contain and the memory contain, I can start testing commands and testing things like joysticks. It becomes a lot easier. And so for you to do that yourselves, if you want to play around with these systems, I always make that available. And so you can download PSX Hello World Advanced here, and you can see you've got a dump of all the register contents here and a dump of any memory address you specify. So if you want to do any testing, if that helps you out, please have a go with it. Okay, so how do we actually assemble our example then? Well, I use a batch file. You can download my build scripts and this pre-configured Notepad++, if you want. If you don't want, you want to make it yourself, that's great. So what I like to do is I like to show you how it works under the hood, so to speak. So we're using this RMIPS assembler here. Basically, there's not many parameters you need to pass with this one, because most of the work is actually being done in the header itself. The specifying of the output file and things is actually being done there. But you know, what we're specifying here, build file in percents here, that is, because it's a batch file, that is actually the source file. So that would be your hello world.asm or whatever your file you're compiling is. Now what I've done next is I've specified this temporary file of listing.txt. Now this is a listing file, which is basically a copy of the source assembly and the resulting bytes and a few other things like the symbols are often in there. It's a debugging thing. You don't need it if you're just starting out. You can't figure out how to get it out. You don't need to worry about it. But if you're really sort of getting into things, it can help you out quite a lot when things don't work the way you expect. Sometimes I've found that the way I'm calculating formulas with regards to symbols and labels isn't being done in the way I thought it would, because the assembler, they scan through the code multiple times, and so the first time they scan through, your values may have your parameters may have values of 0, things like your labels, and sometimes things get weird, and that listing file can really save you from a mess. So if you can get it, please output one. If you can't get it and don't know what one is and you're just starting, don't worry about it yet. And then the other thing, again, another thing you don't necessarily need to worry about, I'm defining a symbol called build PSX, and I'm setting that to 1. Now it calls it a label here, but it's functionally the same as a symbol. And this is for my multi-platform code. I've got routines that will compile to either PlayStation or N64, and the way that is done is with conditional assembly. So there's a check to see if the build PSX is defined, and if it is, it's loading in the PSX module. If N64 is defined, it's loading in the matching N64 module. So again, not something you need, but it's something that I think is worth understanding and knowing about, because being able to have compile multiple versions, maybe you want to have a PlayStation version, an N64 version, maybe you want to have a demo and a full version. You know, if you're selling your game, you want to release a free demo and you only want to have one program to compile, well, you can compile both just with different command lines. So worth looking at. Anyway, now once we've compiled this, we create a binary file, but the binary file can't be executed by our emulator. We're using no cache PSX, and that wants an exe file, which is a slightly different format. Now, what I was doing originally is I was using this bin to exe Python script here. So we've got this script here, we're running it through Python, we're converting prog.bin to prog.exe, and that works very well. So that will create our exe file for us. If you want to do that, go ahead. But if for some reason you don't want to do that, maybe you don't like Python, or you don't want to have Python installed, or you just like doing things as low level as you can. I didn't realize when I did the original tutorials, but actually it's pretty easy. We don't really need that at all. And so if I knew then what I knew now, I wouldn't have used that. I'd have just done it myself. So basically we can actually we can do all the work of the header ourselves here. So we've got this alternate version here, and I've created an alternate script which skips that stage and just outputs straight to the exe. And this is the alternate version. And what we're going to do now is just see what we actually need to do to build the exe directly. So this time our assembler is building the exe all on its own. Now we are having to specify a header which is padded to 800 in hexadecimal bytes here. So we're having to define that, and we're having to specify the start of our program at the same memory address before, and also, because we need to work out the length, the end of our program, and we're padding our file to 2048 bytes here. That's what we're doing there, and so that is padding to 800 in hexadecimal bytes there. So that's the end of our program, and that's just something we've had to do to get this file to be the correct format. Now beyond that, we don't really need to do very much. We just need to put a few bytes in our header that are in the correct format. So we're specifying this PS-X EXE here. That is just a fixed string there. We've got a couple of 0 bytes here. We've got the execution address here, which is the address that the processor is going to call. Well, our first line of the entry here is actual program code, so we just want to execute that. So we're just specifying that address there. And then we've got the load address here, and that is just the start of our program again. So we're just specifying that there. And then we've got the length of our program here. So we're calculating that, program end minus program start. And then all we've got beyond that is a few 0 bytes. And then we've got a few weird values here. Now we're initializing some parameters within the processor itself. And we're loading those with initial values. And so we've got those initial values defined here. And thinking about it, actually, if it's initializing the stack, I guess I didn't need to do it there. Anyway, never mind. I am doing. So no matter. I think I'm loading in probably the same value anyway. So it's not necessarily a problem. But as I say, that's how we can create the header ourselves. Does away with another piece of program. Anything, as far as I'm concerned, anything you can get the assembler to do, get the assembler to do it. You're relying on the assembler anyway. Why rely on other tools that you don't need? So if you don't want to use bin2exe Python, just put something like that at the start of your code. Anyway, there we go. That's all we're covering today. So if you like what you've seen, please like and subscribe, because we'll be coming back to the PlayStation later on. We're going to be looking at more PlayStation fun over the next couple of weeks. So please follow on for that. As I said before, go to the website, get the build scripts, the source code, and everything else on there. And as I would say, welcome to do anything you want with it. If you somehow manage to make the best commercial game in the world and you sell it for $100 billion, you don't need to give me credit even. You're welcome to do that. Hope you enjoyed what you've seen. Thanks for watching, and goodbye.